In the YouTube video titled Lecture 14, The Generalized Discrete Log Problem and the Security of Diffie-Hellman by Christof Paar, Professor Paar elucidates the Generalized Discrete Log Problem, GDLP, and its pertinence to the security of the Diffie-Hellman key exchange protocol. He commences by revisiting fundamental concepts, including discrete logarithms, cyclic groups, and primitive elements, underscoring the significance of generators within cyclic groups. He proceeds to a detailed examination of the Diffie-Hellman key exchange protocol, outlining how Alice and Bob can securely establish a shared secret key over an insecure communication channel. Professor Paar emphasizes the paramount importance of security in cryptographic systems and introduces Oscar, a passive attacker capable of passively observing the communication channel. He delves into the security implications of the Diffie-Hellman key exchange protocol under the assumption of a passive attacker. Professor Paar underscores that Oscar's objective is to surreptitiously compute the shared secret key, denoted as CAB, requiring him to solve the Diffie-Hellman problem, DHP. Professor Paar explicates the inherent connection between the DHP and the GDLP, positing that solving the DHP necessitates solving the GDLP. He elaborates on the computational complexity of solving the GDLP, demonstrating that brute force attacks are feasible for groups of diminutive size but become computationally intractable for groups of substantial size. He subsequently introduces square root attacks, which are computationally more efficient than brute force attacks but still necessitate substantial computational resources. He clarifies that attaining a designated level of security mandates the selection of groups with sufficiently large cardinality. Professor Paar further explores the index calculus attack, a potent attack specifically targeting certain types of discrete logarithm problems. He emphasizes that the index calculus attack poses a formidable threat to Diffie-Hellman systems built upon modular integer arithmetic. Consequently, contemporary Diffie-Hellman implementations employ larger primes or alternative cyclic groups, such as those grounded in elliptic curves, to effectively mitigate the risks associated with index calculus attacks. In conclusion, Professor Paar examines the security ramifications of diverse cyclic groups, encompassing those based on modular integer arithmetic, finite fields, and elliptic curves. He underscores the critical importance of comprehending different attack vectors and judiciously selecting groups with commensurate security levels to ensure the resilience of Diffie-Hellman systems. He concludes by providing pragmatic insights into the deployment of Diffie-Hellman in real-world applications, such as web browsers and electronic passports. From 0 minutes to 5 minutes of the video, Professor Paar begins the lecture by welcoming students back after the semester break and establishing a shared understanding of the course's current position within its 2-semester sequence. He underscores the importance of modern cryptography's 3 foundational components: symmetric algorithms, asymmetric algorithms, and protocols. He emphasizes that the course is currently delving into asymmetric cryptography, particularly focusing on discrete logarithm cryptosystems. Professor Paar then guides students through a review of the discrete logarithm problem, presenting it as a mathematical problem with a specific purpose. He provides a concise definition of a cyclic group and highlights the crucial role of a generator or primitive element. To illustrate these concepts, Professor Paar utilizes the example of the group Z11*, which has 10 elements, demonstrating that a cyclic group is formed when a generator or primitive element can produce all the elements within the group. He then employs the example of Z11* with alpha equals 2 to demonstrate that all elements in the group can be represented as powers of alpha. From 5 minutes to 10 minutes of the video, Christof Paar commences his lecture on the Generalized Discrete Log Problem and Diffie-Hellman by revisiting the Discrete Logarithm Problem, DLP. He employs the illustrative example of Z11*, the multiplicative group of integers modulo 11, and elucidates how the element 2 serves as a generator for the group. This means that all group elements can be generated by raising 2 to various powers. He clarifies that the DLP involves the challenge of determining the exponent x in the equation alpha caret x equals beta mod p, where alpha represents the generator, beta signifies the result, and p denotes the prime modulus. From 10 minutes to 15 minutes of the video, Christof Paar delves into the Generalized Discrete Logarithm Problem and its crucial connection to the security of the Diffie-Hellman key exchange. He begins by providing a succinct recapitulation of the discrete logarithm problem, which essentially entails determining a concealed exponent, denoted as x, given a base alpha, a resultant value beta, and a modulus p. The professor illustrates this concept with a concrete example within the cyclic group Z11*, where the base alpha is set to 2, the result, beta, is 9, and the corresponding secret exponent x is 6. Next, Paar introduces the Diffie-Hellman problem, a cornerstone of modern cryptography. This scenario involves two parties, aptly named Alice and Bob, who are endeavoring to establish a secure shared key despite communicating over a potentially compromised channel. To accomplish this, they employ a public key protocol. Alice chooses a private key A, and Bob selects a private key B. Each party then computes their corresponding public keys. A equals alpha caret A mod P for Alice and B equals alpha caret B mod P for Bob. These public keys are subsequently exchanged between Alice and Bob, enabling them to compute the shared secret key K equals A to the power of B mod P, or K equals B to the power of A mod P. Professor Paar underscores a critical aspect of this protocol. A passive adversary, termed Oscar, can surreptitiously monitor the communication channel and acquire the public keys A and B, along with the public parameters alpha and P. Oscar's objective is to surreptitiously obtain the shared secret key K by calculating alpha caret A asterisk B mod P. The professor then elucidates the fundamental relationship between the Diffie-Hellman problem and the discrete logarithm problem. To breach the Diffie-Hellman protocol, Oscar must effectively solve the discrete logarithm problem, thereby determining either A or B to successfully compute K. This presents a significant computational challenge. Paar explains that Oscar has two primary approaches: brute force or square root attacks. Brute force attacks involve systematically iterating through all plausible values of the secret exponent x, a computationally expensive endeavor that becomes increasingly intractable for larger groups. Square root attacks, on the other hand, offer a more efficient approach, requiring SQRT n steps, where n represents the size of the underlying group. For instance, to achieve a robust 80-bit security level, meaning an attacker would need to perform 2 to the power of 80 operations to compromise the system, the group size n must be at least 2 to the power of 160. Paar cautions that there exist even more formidable attacks, such as the index calculus attack, specifically targeting certain classes of discrete logarithm problems. Professor Paar concludes by emphasizing the necessity of employing larger primes p and a larger value for 2 to the power of m in practical Diffie-Hellman implementations to effectively thwart adversaries employing index calculus techniques. In real-world cryptography, key lengths of at least 1024 bits are widely employed for secure communication, with a strong preference for even larger key sizes. From 15 minutes to 20 minutes of the video, the speaker delves into the paramount importance of security within the realm of cryptography, focusing specifically on the Diffie-Hellman key exchange protocol. The speaker emphasizes the necessity of introducing a malevolent entity, dubbed Oscar, who epitomizes a passive adversary. This adversary possesses the capability to passively monitor the communication channel but is restricted from actively interfering with the exchanged messages. The speaker subsequently elucidates the robustness of the Diffie-Hellman protocol against such passive attacks. Oscar, despite possessing knowledge of the shared domain parameters, including alpha, p, and the public keys of Alice and Bob, remains bereft of access to the critical private keys of Alice, A, and Bob B. The speaker posits that to compromise the protocol's integrity, Oscar would need to computationally determine the session key cab, which is derived by raising alpha to the power of A asterisk B by solving the computationally challenging discrete logarithm problem. This problem necessitates the recovery of the private key values, A or B, from their corresponding public keys. From 20 minutes to 25 minutes of the video, Professor Paar delves into the intricacies of the Diffie-Hellman problem, a cryptographic conundrum that hinges on the interplay of known and unknown parameters. The objective of an adversary, aptly named Oscar, is to surreptitiously acquire the elusive cab parameter, representing the shared secret key. Oscar is assumed to possess a formidable arsenal of information, including alpha, p, and the publicly accessible keys of Alice and Bob, denoted by alpha raised to the lowercase A mod p, and b, alpha raised to the lowercase b mod p, respectively. Paar clarifies that to unveil cab, which is computationally equivalent to alpha raised to the product of lowercase a and lowercase b mod p, Oscar must cunningly deduce either lowercase a or lowercase b. One potential strategy for resolving the Diffie-Hellman problem entails computing the discrete logarithm of either uppercase a or uppercase b, thereby uncovering the private key of either Alice or Bob. The discrete logarithm is determined by identifying the exponent x that fulfills the equation alpha raised to the x mod p equals uppercase a or uppercase b. This process demands a brute force approach, systematically testing every conceivable value of x until the correct one is unearthed. Paar underscores the criticality of employing sufficiently large values for n, the cardinality of the group, to render brute force attacks computationally prohibitive. For instance, achieving an 80-bit security level necessitates a group size of at least 2 raised to the 80th power. This illuminating observation underscores the crucial role of employing larger prime numbers or field sizes in real-world cryptographic implementations to ensure the robustness and confidentiality of communications. From 25 minutes to 30 minutes of the video, the speaker delves into the Diffie-Hellman DH problem, a cryptographic challenge intimately connected to the discrete logarithm problem. He posits that the DH problem necessitates a set of public domain parameters, including the generator alpha and the modulus p, which are disseminated within the cryptographic community. Alice and Bob, the entities participating in the protocol, each generate their private keys, denoted by lowercase a and b respectively, and subsequently compute their public keys, symbolized by uppercase a and b, by exponentiating alpha using their private keys modulo p. Specifically, Alice calculates b to the power of a mod p, while Bob calculates a to the power of b mod p. Remarkably, despite the independent computations, Alice and Bob converge upon the same shared secret key, k, which is equivalent to alpha caret a asterisk b mod p. The speaker underscores the paramount importance of security within cryptography, emphasizing the imperative to safeguard this shared secret key, k, from the machinations of Oscar, the nefarious attacker. He introduces the concept of a passive adversary, an attacker who can merely observe the communication channel without the ability to tamper with the exchanged messages. The speaker emphasizes that the security of the DH protocol hinges upon the intractability of solving the discrete logarithm problem. From 30 minutes to 35 minutes of the video, Professor Paar delves into the security considerations of the Diffie-Hellman key exchange protocol, emphasizing its paramount importance in contemporary cryptographic practices. He introduces a hypothetical adversary, Oscar, who seeks to compromise the protocol by surreptitiously acquiring the shared session key. Oscar's objective is to calculate the session key, represented by cab, which is alpha raised to the power of a asterisk b, without the possession of the private keys a and b. To achieve this, Oscar must solve the discrete logarithm problem, necessitating the computation of either private key a or b by determining the logarithm, with base alpha, of either a or b modulo p. This task presents a formidable computational challenge, particularly when dealing with substantial prime numbers. Paar elucidates the practical ramifications of these attacks, positing that a swift resolution of the discrete logarithm problem would severely undermine the security of Diffie-Hellman systems. He then introduces the concept of square root attacks, which provide a computationally efficient method for solving the discrete logarithm problem, but only for a specific bit length. Consequently, the DES algorithm utilizes a key length of 56 bits, as a larger key size would be susceptible to these attacks. Paar further delves into the index calculus attack, a powerful cryptanalytic technique specifically engineered to compromise certain types of discrete logarithm systems. To bolster security against this attack, larger prime numbers must be employed. Paar underscores the practical implementation of these insights, noting that, in real-world scenarios, larger prime numbers, frequently in the range of 1024 bits or greater, are utilized to fortify security against the index calculus attack. Paar concludes this segment by dissecting the index calculus attack, a sophisticated cryptanalytic method that particularly targets modular P arithmetic. This attack, requiring significant computational resources, emphasizes the necessity of employing even larger prime numbers, often ranging from 1024 to 2048 bits, to ensure robust security. Paar's discourse highlights the indispensable role of robust cryptographic protocols in safeguarding sensitive information, unveiling the intricate interplay between mathematical concepts, security vulnerabilities, and real-world applications within the domain of modern cryptography. From 35 minutes to 40 minutes of the video, Professor Paar transitions from a review of foundational concepts to an exploration of the crucial aspect of computational hardness in cryptography, emphasizing its paramount importance alongside functionality. He provocatively asks the audience to consider the additional requirements for a secure cryptosystem beyond mere functionality. The answer, he underscores, is the paramount concern of security. The crux of a cryptosystem's security lies in the assumption of a computationally limited adversary. This adversary, often referred to as Oscar, is modeled as a passive eavesdropper incapable of manipulating the communication channel. Professor Paar then dissects the attack to compromise a cryptosystem, the computation of the shared secret key, designated as CAB. He reveals that to achieve this, the attacker must solve the computationally challenging discrete logarithm problem, denoted as DLP. This moment highlights the inextricable link between the Diffie-Hellman key exchange protocol and the discrete logarithm problem. Solving the Diffie-Hellman problem, he asserts, inherently implies the ability to solve the DLP. Professor Paar further emphasizes the significance of employing sufficiently large prime numbers, specifically p, in safeguarding a cryptosystem. He asserts that p must be at least 2 to the power of 80 bits long to effectively thwart brute force attacks. However, he cautions that this merely represents a minimal security threshold, as a panoply of more sophisticated attack methods exist. This is where the notion of square root attacks emerges. Square root attacks capitalize on the intrinsic complexity of the discrete logarithm problem, characterized by O(sqrt) n, computational time, where n denotes the cardinality of the underlying group. He elucidates the efficacy of square root attacks, demonstrating their ability to dramatically reduce the complexity of the DLP to 2 to the power of 40 steps, easily executed on commonplace laptops. Consequently, he underscores the necessity of employing larger primes, typically around 1024 bits, to effectively counter these more potent attack vectors. This underscores the ever-present need to remain vigilant against evolving attack strategies, and to continuously adapt security measures to maintain the resilience of cryptosystems. From 40 minutes to 45 minutes of the video, Professor Paar delves into the concept of the Generalized Discrete Logarithm Problem, GDLP, as a method for extending the scope of the Diffie-Hellman key exchange. He emphasizes that while the Diffie-Hellman key exchange is traditionally implemented using modular arithmetic, its application can be broadened to encompass other cyclic groups, including the intriguing realm of elliptic curves. Professor Paar highlights that the GDLP possesses the potential to construct cryptographic systems that transcend the limitations of modular integers. He underscores the paramount importance of employing secure cryptographic systems, which are characterized by their resistance to an adversary's attempts to compute the session key. To illustrate the security considerations, Professor Paar introduces a hypothetical adversary named Oscar, who represents a passive eavesdropper with limited capabilities. Oscar possesses knowledge of numerous protocol parameters, including the publicly accessible domain parameters and the public keys of Alice and Bob. However, Oscar lacks access to the session key, CAB. Professor Paar establishes that Oscar's primary objective is to determine the value of CAB. He elaborates that achieving this objective necessitates Oscar's successful resolution of the GDLP. From 45 minutes to 50 minutes of the video, Professor Paar delves into the concept of the Generalized Discrete Logarithm Problem, GDLP, emphasizing its broader applicability beyond the confines of the multiplicative group of integers modulo a prime ZP star. He elaborates on the notion that within a cyclic group characterized by an element alpha, all group elements can be expressed as powers of alpha. Professor Paar then proceeds to introduce a formal definition of the GDLP. Specifically, given a cyclic group G equipped with a group operation, a primitive element alpha, and an element beta belonging to G, the task is to identify an integer x such that alpha raised to the power x, utilizing the group operation, yields beta. He emphasizes that this generalized form of the discrete logarithm problem encompasses a broader range of scenarios, with the operation employed for computing alpha to the power x potentially being either additive or multiplicative. Professor Paar underscores that this choice of operation dictates a shift in notation. In scenarios where multiplication serves as the operation, the notation remains as alpha raised to the power x. Conversely, when addition constitutes the operation, the notation assumes the form x times alpha, where x quantifies the number of times the addition operation is performed. From 50 minutes to 55 minutes of the video, Professor Paar delves into the concept of the Generalized Discrete Logarithm Problem (GDLP), emphasizing its broader applicability beyond the confines of ZP*. He elucidates that GDLP can be effectively employed with a diverse array of cyclic groups, thereby expanding its potential in cryptographic applications. To illustrate the intricacies of GDLP, Professor Paar presents a compelling example featuring a cyclic group G, where the group operation is symbolized by the enigmatic donut. This non-standard notation, he clarifies, represents either additive or multiplicative operations, depending on the specific nature of the group. Continuing with the example, Professor Paar introduces alpha, a generator or primitive element, and beta, an element residing within the group G. The core of the GDLP lies in determining an integer x that satisfies the equation beta equals alpha asterisk alpha asterisk alpha x times. The asterisk symbol denotes the group operation, which, as previously stated, can be either additive or multiplicative. Professor Paar elaborates on the notation variations inherent to GDLP. When the group operation is multiplicative, the equation is elegantly expressed as beta equals alpha caret x, where alpha caret x signifies alpha raised to the power of x. Conversely, in the case of additive group operations, the equation takes the form beta equals x asterisk alpha, where x asterisk alpha represents alpha multiplied by x. Professor Paar underscores that the notation for GDLP undergoes a significant transformation depending on the group operation. If the operation is multiplicative, the equation is presented as beta equals alpha caret x. However, if the group operation is additive, the equation assumes the form beta equals x asterisk alpha. This potential for notational ambiguity can pose challenges for students new to the subject and will be further explored in the context of elliptic curves, which will be discussed in detail during the upcoming lecture in 2 weeks. From 55 minutes to 60 minutes of the video, the speaker embarks upon a discourse concerning the Generalized Discrete Logarithm Problem (GDLP), emphasizing its paramount significance in the realm of contemporary cryptography. He expounds upon the GDLP's efficacy as a versatile instrument for the construction of cryptographic systems. The speaker underscores that the GDLP transcends the confines of modular arithmetic, extending its applicability to encompass other cyclic groups, including the intriguing domain of elliptic curves. This generalized approach serves to enhance both flexibility and robustness within the cryptographic landscape. Furthermore, the speaker asserts that despite its theoretical underpinnings, the GDLP possesses tangible practical relevance. The speaker embarks on an exploration of specific attack vectors directed at discrete logarithm systems, including the rudimentary brute force attack and the more sophisticated square root attack. He elucidates that square root attacks exhibit a computational complexity of O square root n, where n represents the cardinality of the group. This observation underscores the imperative to employ groups of substantial size to ensure the security of cryptographic systems. Finally, the speaker introduces index calculus, a formidable attack that specifically targets certain types of discrete logarithm systems, necessitating the utilization of even larger key lengths to effectively mitigate the risks posed by such attacks. From 60 minutes to 65 minutes of the video, Professor Paar embarks on a detailed exposition of index calculus attacks. He asserts that these attacks are computationally potent, yet their effectiveness is contingent upon the specific type of discrete logarithm problem targeted. Specifically, index calculus attacks are documented to be efficacious against both ZP** and GF, 2 to the power of m, finite fields. He highlights that the formidable nature of these attacks constitutes a primary reason for the widespread adoption of 1024-bit key lengths in web browsers, despite the feasibility of smaller primes for safeguarding against brute force attacks. Professor Paar emphasizes that the computational complexity of index calculus attack scales with the square root of the group order, resulting in a requirement of 2 to the power of 40 operations for a group of size 2 to the power of 80. This translates into the capacity to breach 160-bit systems using a contemporary laptop. To illustrate this point, Professor Paar cites the successful compromise of a 532-bit system in 2007. This underscores the imperative for utilizing large primes, typically at least 1024 bits, in practical cryptographic implementations. From 65 minutes to 70 minutes of the video, the speaker delves into the critical realm of attacks on discrete logarithms, emphasizing their paramount role in determining the requisite key length for robust cryptographic systems. He elucidates that brute force attacks, while conceptually simple, necessitate a substantial number of operations, precisely n operations where n denotes the order of the group. This implies that achieving an 80-bit security level mandates a group order of at least 2 to the power of 80. Subsequently, the speaker introduces the more sophisticated square root attacks, which exhibit enhanced efficiency by reducing the computational complexity to the square root of 2 to the power of 80, equivalent to 2 to the power of 40. This dramatic reduction in computational effort renders an 80-bit security level insufficient for practical applications. The speaker underscores the imperative for employing more substantial key lengths, such as 160 bits or even 1024 bits, to effectively mitigate these attacks and maintain security. The speaker then introduces the formidable index calculus attacks, which are particularly potent against specific types of discrete logarithm problems, notably those utilizing ZP* and GF, 2 to the power of m, groups, commonly employed in contemporary web browsers. To counter these advanced attacks, the speaker emphasizes the necessity of adopting significantly larger key lengths, generally a minimum of 1024 bits, to ensure robust and long-term security in cryptographic systems. From 70 minutes to 75 minutes of the video, Christof Paar delves into the security of the Diffie-Hellman key exchange protocol, emphasizing its reliance on the computational intractability of the discrete logarithm problem. To compromise the Diffie-Hellman exchange, an adversary, denoted as Oscar, must ascertain the shared secret key, CAB, which is calculated as alpha raised to the power of a modulo p. Oscar possesses access to all public parameters, encompassing alpha, p, the public keys a and b, but lacks knowledge of the private keys a and b. Paar outlines two primary attack vectors against the discrete logarithm problem: brute force and square root attacks. A brute force approach involves iteratively testing all potential values of x within the equation alpha raised to the power of x equals beta modulo p until the correct solution is identified. This method necessitates n computational steps, where n represents the cardinality of the underlying group. From 75 minutes to 80 minutes of the video, Professor Paar delves into the computation of the discrete logarithm problem. He revisits the notion of a primitive element, an element capable of generating all other elements within the group, and elucidates the fundamental properties of such elements. He then proceeds to expound upon the Diffie-Hellman key exchange protocol, a method enabling two parties to establish a shared secret key via an insecure channel. The protocol's security relies heavily on the computational complexity of the discrete logarithm problem, rendering it a highly secure method. Professor Paar subsequently introduces the Generalized Discrete Logarithm Problem, expanding its application beyond the confines of ZP* to encompass any cyclic group. This generalization opens doors for the utilization of diverse groups, such as elliptic curves, in the construction of cryptographic systems. He emphasizes the importance of selecting sufficiently large groups to mitigate the effectiveness of attacks, such as the index calculus attack. Specifically, when employing elliptic curves, it is imperative to use a minimum of 160 bits to ensure resistance to these potent attacks. Professor Paar concludes his discourse by underscoring the significance of comprehending these attacks to fully grasp the inherent strengths and weaknesses of various cryptographic systems. From 80 minutes to 85 minutes of the video, Professor Paar elucidates the nature and implications of index calculus attacks, a formidable class of attacks that specifically target certain discrete logarithm problems. These attacks are particularly efficacious against the first two groups discussed in the lecture: the multiplicative group of integers modulo a prime, z sub p, /sub, sup, asterisk, /sup, and the multiplicative group of polynomials over gf, 2, gf, 2 sup m, /sup, sup, asterisk, /sup, Professor Paar underscores that these attacks are not universal, but rather exhibit a pronounced specificity to these particular groups. He then proceeds to elaborate upon the security implications of these attacks, emphasizing that their potency necessitates the utilization of a sufficiently large bit length for secure communications. To achieve 80-bit security against index calculus attacks, a group size of at least 2 sup1/60th/sup elements is indispensable. This translates into the employment of 160-bit numbers to represent the group. Professor Paar cogently underscores the imperative of employing adequately large bit lengths to effectively thwart these attacks. This explains why cryptographic systems in practical deployments frequently employ a minimum of 1024 bits to ensure robustness against such threats. He even ventures to suggest that intelligence agencies such as the NSA might possess the computational capabilities to manage even larger bit lengths, potentially exceeding 1024 bits by a few hundred bits. He further presents a historical table showcasing the breakdown of discrete logarithm problems, illuminating a discernible pattern of escalating bit lengths being successfully attacked over time. The most recent discrete logarithm problem successfully breached was in 2007, involving 532 bits. Concluding this section, Professor Paar offers a concise overview of index calculus attacks and their relevance to real-world cryptography. He emphasizes that these attacks may not be as widely recognized or discussed as other attacks, but they nonetheless constitute a substantial security vulnerability. He recommends the Handbook of Applied Cryptography as a valuable resource for those seeking to deepen their understanding of this specific attack methodology. The lecture concludes with a succinct reminder of the paramount importance of employing secure cryptographic systems and the imperative of remaining cognizant of various attacks, including those that may not be widely publicized. From 85 minutes to 88 minutes of the video, the speaker transitions to a more sophisticated discussion of the third type of attack on the DLP, the index calculus. He emphasizes the potency of these attacks, highlighting their efficacy against specific types of discrete logarithm problems, including the DLP prevalent in web browsers. The speaker clarifies that index calculus attacks are not universally applicable, but exhibit a predilection for certain groups, such as the ZP** and GF, 2 to the power of m, groups. He provides a concrete example of the attack's effectiveness, citing the 2007 breach of a 532-bit DLP. He speculates that intelligence agencies possess the resources to successfully mount attacks against even larger DLPs, potentially those with 600 or 650 bits. The speaker attributes this capability to the superior computational power and refined algorithms likely available to these agencies compared to those within the research community.